Good morning and welcome to Wednesdays with Mr. Longmire. Today we're going to be looking at ionic formulas and ionic charges and how to write the ionic formulas. So today we're going to be starting with your famous and lovely balancing ionic formulas. I made this PowerPoint for you to sort of help ease you guys into it. So yeah, we might as well make a start. Today we're going to be talking about the yin and the yang of electric charges and how all that relates to chemistry. Right? Nice, easy, beautiful and lovely. Next. Lovely. So, ionic formulae. So as you've so far covered, you know that atoms aren't always the most stable because of their electron configurations. As we put electrons into their shells, we can put them in the order of 2 in the first shell, 8 in the second, 8 in the third, and 8 in the fourth. And then we stopped right there at calcium, element number 20. We're not going to go any further. But as we know that as we sort of start adding electrons to these shells, sometimes the shells aren't always full, right? So with lithium, we've got 2 electrons in the first shell and 1 electron in the second shell. That 1 electron sitting there by himself in the second shell there isn't exactly the most happiest. So unfortunately, lithium is going to be very eager to lose that 1 electron. When lithium loses that 1 electron, it's still got the 3 protons it has inside of the nucleus, because in chemistry we don't touch the neutron. That's what the physicists do. That's their territory. We don't touch that. Instead, we're going to be playing with the electrons instead. So because lithium has just lost its outermost electron from the second shell, it still has got the 2 electrons in its first shell, but it's got the 3 protons in the nucleus still. Each of the protons is worth 1 positive charge, and each of the electrons is worth 1 negative charge. So this means that we've now got an uneven distribution of charge within our atom, right? Or now, should I say, ion. So because the lithium atom has got 3 protons, it has got a positive 3 charge from its nucleus. And now since it's lost 1 electron, it's only got 2 electrons left, and each electron gives it a negative 1 charge. Right? So our lithium ion now, remember an ion is a charged atom, or an atom with a positive or negative electric charge. Lithium ion is going to be positive 1, because it's got 1 more positive charge than it does negative charges. It's got a positive 3 from the nucleus, from the protons, and a negative 2 from the 2 of the electrons that are left. Alright, so that's electron configuration sorted and how we're forming our ions. Now, ions do like to kind of stick together if they've got positive and negative charges. Your cations are always going to be positive and your anions are going to be negative. Now, because of electrostatic forces and a whole bunch of jibber jabber like that, your positives are going to be attracted to your negatives. So as they get sort of close to each other, they're going to be sort of sucked in, and they're going to come together and kiff, right? If you've got 2 positives, however, they're going to be repelled or pushed apart, right? Like charges repel each other. If they're 2 negatives, of course, they're also going to be repelled as well. So 2 chlorine or 2 chloride atoms the 2 chloride ions don't want to be too close to each other. However, if you've got, say, your lithium ion, which is 1+, and your chloride ion, which is 1-, they are oppositely charged and they're going to be mutually attracted towards each other. So they're going to kind of go together and kiff like that, right? This is an ionic compound, and your ionic compounds always have a net 0 ionic charge. This means that your positives and your negatives have to actually cancel out, right? This means that you need to have enough of your positives to cancel out all your negatives, and you've got to have enough negatives to cancel out all your positives, right? We always write down your ionic formulae or your ionic compounds as it being neutral. This is why when you see sodium chloride or NaCl, you don't see any positive 1s or negative 2s or whatever next to it. Both the 1 positive and the 1 negative from each of the ions cancel each other out and make it neutral or 0. Alright, so as I was just talking about, sodium chloride, right? Your sodium ion has got a positive 1 charge, your chloride ion has got a negative 1 charge. Now we need to sort of write out, an ionic sort of formula for this. Right? So the way we write these out is we've got to find the right ratio between sodium ions and chloride ions. Right? So because in this case both of them have got a positive 1 and a negative 1 charge, they're going to be attaching or bonding to each other in a 1-to-1 ratio. Right? Because I've got only a 1 positive charge and a 1 negative charge, I only need 1 of each at this point. So it's 1 sodium, 1 chloride. It's easy, it works, right? It just works. The formula for sodium chloride in this case is just going to be NaCl, right? That's the formula for sodium chloride. Sodium is Na, chloride is Cl. We don't need to write the charges there because they've already been cancelled out at this point. And we don't need to write any like 1s or 2s underneath any of the atoms there, or one of the symbols there, because there's only one of them. And sort of just like in algebra, we don't write, 1x, we just write x. If we have like 2 of them though, we do want to say 2x, or we've got 2 of x. However, as we sort of move on to sort of different ions, we get kind of these more difficult questions coming up. So for this particular case here, I've got magnesium sulfate. This is something they use for Epsom salts. You can buy it in your local supermarket, and people like putting it in their bath water. Yep. Try exporting that. So magnesium is Mg2+, right? It is your magnesium metal, and it has lost 2 electrons. This gives it a positive 2 charge. Sulfate is a polyatomic ion, which is just a fancy word for saying it's got more than 1 atom, and we can always come back to that one later, but we basically just treat it as a single unit or a single particle in this case. And your sulfate has got a charge of -2, right? So in this case here, we need to make sure that our +2 from our magnesium and our -2 from our sulfate are balanced out. Otherwise, we're going to be left with a molecule, or sorry, a ionic compound with a net charge, and we don't want that. We want all of my positives and all of my negatives cancelled out here. So we're going to try to find the ratio of magnesium to sulfate that will do this for us, right? Remember, we want to get a neutral or net 0 charge ionic compound at the end of this. In this case, again, it's reasonably easy because just like sodium chloride, we just need a 1-to-1 of each of them, luckily enough, right? So because magnesium's got a 2+ and sulfate has got a 2-, right? We just need 1 of each to balance this out. So +2 minus 2 is just going to be 0 in this case, right? I've got 2 over here, I've got -2 over here. They balance out because I've got 2 positives and 2 negatives on each side. They balance out, and it's nice and easy and good, right? So we're going to need 1 of each ion in order to make a neutral compound. The formula for magnesium sulfate is just going to be MgSO4. As you can kind of see, we've got our Mg there representing magnesium. There's no number after that one, so it's just saying we've got 1 magnesium ion there. We've also got SO4, which is your sulfate ion there, right? And as you can see, we don't need to have any brackets here because they're just a normal, because there's just 1 of each at this point. We don't need to be playing around with any of the numbers. And the charges have magically disappeared because we're saying this is a neutral ionic compound. We don't need to write the charges because at this point they've been balanced out, right? There's no net charge there overall. Alright, we can get into some more complicated ones as well. So this one is sodium carbonate. This one is used for washing soda. You may or may not have this stuff sort of in and around your house. It is probably something that you may have encountered every now and again. No, it is not edible. It is an ionic compound made of sodium and carbonate ions. Sodium, as we were talking about before with our sodium chloride, is Na positive or Na+, and carbonate is another polyatomic ion of CO3 2-, right? Again, we're going to be treating it as if it was just a normal particle, which is a normal ion, and we're just going to be doubling it or tripling it or playing around with it as we kind of need, right? So for this particular case, we need to make sure that we've got enough positive ions to balance out our negative ions. In this case, your carbonate, or your anion, your negative ion, is going to take the prime role here because it has got the biggest charge, right? We need to make sure that we balance out all -2 of its electric charge in order to make a neutral ionic compound. We've got sodium to work with this, right? So if we just have one sodium and one carbonate, we're still not going to be able to balance out the charge anymore. So it's not going to be a 1-to-1 ratio because if you've got a -2 charge and a +1 charge, then your -2 is going to outweigh your +1, right? We need at least 2 positive charges to cancel out our carbonate here, right? So we need at least 2 positive charges. The only way to get 2 positive charges, because each of our sodiums only have got a +1 charge, is to have 2 sodium ions here, right? So our ratio is going to be 2 sodium to 1 carbonate, right? So we've got a 2-to-1 ratio here, right? We can write this down as such. The formula for magnesium sulfate is going to be Na2CO3. So because we've got 2 sodiums to balance out our 1 carbonate here, we're going to be needing, I've put a little sort of 2 directly after your sodium. I've just realized that there is an error in my PowerPoint, and I did not change magnesium sulfate to sodium carbonate. So enjoy that little snuffer of mine. But so the formula there is correct, Na2CO3. The little 2 there indicates that there are 2 sodium atoms there, right? Or 2 sodium ions. So that's where we're getting our +2 charge from, and our carbonate is going to be -2. So we've got 2 positive ones and 2 negative charges there. And that's going to cancel out for a net charge of 0. So our ionic compound is going to be neutral. Remember, all of our ionic compounds need to be neutral, otherwise they're not going to be an ionic compound, right? So the whole goal of this is finding the right ratio between your positives and your negatives, so that you can find a set of numbers there that cancel each other out and arrive at a net neutral number, i.e. 0. We can keep going with aluminium oxide. Now this one is going to be a bit more of a difficult one for this one, unfortunately. So aluminium oxide is pretty much the ore of aluminium. Aluminium comes as a +3 ion, right? So +3. So this one's a big boy. Aluminium has got the electron configuration of 283, which means that it has got 3 electrons in its outermost shell. It's easier for aluminium to lose those 3 electrons than it is to gain an extra 5, right? So it's going to drop those 3 electrons as quickly as Gamora off a cliff, and it's going to be left with a +3 charge, which is quite a bit as ions go, right? Oxide, however, is just oxygen. It's got the configuration of 2-6. So we want to get the configuration of 2-8 for our oxygen. To do this, we need to add 2 electrons to the outermost shell. So we go from 2-6 to 2-8, right? So we're going to have 2-8 in our outermost. 2-8 as an electron configuration with 8 electrons in your outermost shell. This means that your oxygen has gained 2 electrons, which means that overall it's going to have a -2 charge, right? So we've got our aluminium ion, which is Al3+, and our oxide ion, which is going to be O2-. So now we need to find the right ratio of sort of how to balance these 2 out, right? We need to make sure that we know sort of how many of each we need and the right ratio. So I'm just going to go through and explain this one to you because it's easier said than done. Basically, the idea with this one is if you have 1 aluminium and you add 1 oxygen, you're going to have, still going to have a +1 charge there. If you add an extra oxide, so you've got 1 aluminium and 2 oxides, and a 1-to-2 ratio, then you're going to have too many negative charges there. So you're not going to find the right ratio if you're just going to stick with 1 aluminium. Right? So instead what we're going to do is find the lowest common multiple of 3 and 2, right? Which happens to be 2 and 3, quite funnily enough. So it's going to be 6. So if we have 2 aluminium and have a net positive charge of +6, right? 2 aluminium, 2 times 3 is +6. And we've got 3 oxides, so it's going to be a net negative charge of 3, of 6. -6, so that's -2 times 3 is going to be -6. This means that we've got 2 aluminiums and 3 oxides there, and and if you run the numbers, we've got the same number of positive charges as we do negative charges. We've got positive 6 positive charges from our aluminium and negative 3 charges from our oxide. These will cancel out and will give us neutral ionic compound at this point. The formula for, again, I have not changed the name. I still wrote magnesium sulfate down the bottom when it should have been aluminum oxide. My snafu once again. The formula though is correct, Al2O3. What we have written there says that we have got 2 aluminium ions and 3 oxide ions. The 2 in little subscript after the Al means that there are 2 of them, and the 3 after the oxygen, the little subscript down there, the one that kind of sits just sort of on the bottom of the line and then a little bit below, that's called subscript. That tells you that there are 3 oxide ions there. Alright, so we've got 2 aluminium atoms, 3 oxide atoms, and our formula is going to be Al2O3. Alright, Al2O3. Alright, so just to double check to make sure that you guys are happy when it comes to writing out these ionic formulae, we use superscript, which is pretty much just it being above the line, or a little bit on top of the line and a little bit above, to show charge. So if we go back to here, you can see that our aluminium, this, give me a moment, this little boy here, right, this little positive 3, you can kind of see how it's kind of above the line and is a little bit smaller, right? That's your superscript, or your charge basically. So what we're trying to explain with this little sort of little bit here is saying that our aluminium ion has got a positive 3 charge. Right? Now, if we keep going, subscript is pretty much just used to show how many there are. This is kind of like putting the number in front of a variable in algebra. It's just saying, hey, I've got this many of whatever this is. So if we go back to, say, aluminium and oxide, right, this little 2 here is meant to represent that we have got 2 aluminium. So this 2 means I've got 2 of these, or 2 Als, right? So 2 particles of aluminium. And this little 3 down here, this little subscript, is meant to say that there is going to be 3 particles of this oxide here, right? So I've got 2 Als and 3 oxides, right, or 3 O's in this case. We can also use brackets, and this is used for polyatomic ions. So if we're going back to, say, we'll go back to, say this one here, carbonate. Carbonate, as I mentioned before, was a polyatomic. Poly means many, atomic means atom. So it's an ion that's made up of multiple atoms. It looks a bit more complicated and scary and all that kind of stuff, but really we just treat it the same as we do, like your chlorides or anything like that. Right? So if you're going to make sodium chloride here, there we go. Right? We just write NaCl. We do the same thing when it comes to, say, your carbonate. We just put it on afterwards. The only issue is if we were to have multiple of your carbonates, your CO3, right? If we were to have, like, say, 2 of them, we would have to write that as CO3 2, and we'll put a little 2 after your, CO3. The issue with this being that if you were to put a little 2 after the 3 here, what you're basically saying there is that you've got 1 carbon and 32 oxygens, which is going to be a little bit of a problem. So if I put a little sort of 2 there, right, you can see that, hey, now I've got 1 carbon, 32 oxygens, which is not going to be the case because you can only have carbonate with 3 oxygens and 1 carbon. So what we do instead is we put brackets around your ion, right, or your polyatomic ion. So these brackets here are basically saying, hey, I have got 2 of whatever's in here, which means that I now have got 2 carbonates. So what I'm trying to represent here is that I've got, in total, 2 carbons and 6 oxygens, right? So I'm saying that I've got 2 carbonates, 2 CO3, 2 CO3, right? I've got 2 of these guys, right? And they're off just doing their own thing there. And back to it. Lovely. So down the bottom here we have got your little sort of script for ammonia, which is NH3. This is saying that we have got 1 nitrogen, right? So ammonia is made of 1 nitrogen. And the little subscript after your hydrogen there is meant to say that we have got 3 hydrogens, right? So 1 hydrogen, 2 hydrogen, 3 hydrogen, right? And if you were to look up, say, a molecule of ammonia, right? Something sort of nice and easy. Just bring this up on the other screen. Ooh, there we go. There we go. Right. So that's basically what your ammonia is meant to look like. So this, NH3 sort of script here, or this NH3, writing is meant to represent, this molecule here. We've got 1 nitrogen atom surrounded by 3 hydrogen atoms, right? 1 N there, 3 hydrogen around it. That's what the little sort of 3 is meant to represent, and yeah, that's pretty much what the script is. So it's like chemistry shorthand or chemistry algebra, pretty much, right? And it's much easier to write NH3 because it's just basically 3 letters or 2 letters in a number, than having to write out ammonia every single time, right? Plus, yeah, it's just easier for us, and you get used to using it quite a bit. Right, moving on. Next one. Lovely. So we also have to make sure that we go through and balance out these formulae properly. So when you're writing your ionic formulas, you've got to make sure that your charges of your cations, which are your positive ions, and your anions and your negative ions, balance out, and they reach a neutral number. So they need to basically reach 0 at this point, right? So we need to write all of our compounds as neutral compounds, or the positives need to balance out your negatives. Now you can do this through just trial and error, right? You can literally just guess and then plug the numbers in and see if it works. So if I go all the way back to, say, I don't know, we're going to be going back to, say, sodium chloride, right? Through a bit of trial and deduction, doing a bit of Sherlock Holmes there, you could probably figure out that you need 1 positive and 1 negative to cancel them out to make 0, right? So there we go. You could probably do that. That one is reasonably straightforward. Your magnesium sulfate, once again, you can probably work out that you need 1 magnesium and 1 sulfate in order to get that one to work, right? So positive 2 and negative 2 to make 0. You can kind of work that one out, right? It's not, exactly rocket science. Yeah, you can trial and error your way through this. You can literally brute force it, and it will work. When you get to, say, this one here, when you're dealing with sodium carbonate, again, you can, make the deduction, Mr. Holmes, that you need 2 sodiums for every 1 carbonate, because sodium's got a positive 1 and carbonate's got a negative 2, and you could probably brute force your way through that. Now, aluminium oxide with your Al positive 3 and oxide 2 minus, that one's going to be a little bit more tricky or difficult, right? This one is considered, pretty much an excellence level thing at level 1. So this is quite a tricky one. However, you can quite easily do this by using a quick little trick that, chemistry teachers don't want you to know. We call this the drop and swap method, right? Basically what you do is you take the charge of one of your atoms, or so one of your ions. In this case, we're going to be dealing with, say, lead 3. Pb is lead. We've got a positive 4 up here. Sorry, I meant to say lead 4. So we've got lead 4 up here. Right? It's got a positive 4 charge, and we've got oxide over here with a negative 2 charge. Right? So we identify what it is that we're doing, what ions we're dealing with, and we make sure that we identify what the charges are going to be. The next step of this method is to drop your ionic charges, right? So what we're going to do is we're going to be taking your positive 4 and you're going to be moving it down here to the subscript of your oxide, right? So we're going to write down, 4 here. We're stealing the 4 up here and we're dumping it down here where your oxide is. We're also going to be doing the same thing with your negative 2 on your oxide, and you're dumping it down to the bottom of your lead. So we're taking the 2 from that and we're putting that one down there, right? And when we do that, we just cross out the charge because, YOLO, right? We don't need that anymore, right? We just are interested in the subscript. So once you've taken the superscript and you've dropped it down, then you can get rid of it. We're now left with this little abomination here. So this is Pb2O4. What we're trying to say here is that we've got 2 lead and 2 lead 4 and 4 oxygens here, right? Now you could leave it at this, and technically this is a neutral compound. I mean, after all, you know, lead, you've got 2 of them there. It's got a positive 4 charge, and you've got your oxide there. There's 4 of them. There's a negative 2 charge. So overall, you've got positive 8 and negative 8. They do cancel out, right? They do make 0, and they do make a neutral compound. However, we could simplify this one down a little bit further by pretty much, you know, dividing by the lowest common denominator. In this case here, we can drop down, you know, your lead just down to Pb. So we can half the 2 to 1, right? Because it's basically an invisible 1 right there after the Pb at the bottom. And we can drop the 4 down to a 2. So we're just simplifying it, right, to make it a little bit sort of easier. Right? If we can simplify it, we will. Basically what we're trying to say is we need, for every 1 lead or every 1 lead 4, we need 2 oxides. So the lead has got a positive 4 here, right? And your oxide, there's 2 of them, right? So each of them have got a negative 2 charge. So overall, it's going to balance out to a nice big fat 0, right? And our ratio is going to be 1 to 2. So 1 lead, 2 oxides. And that is your ionic formula. And that's all been balanced, so it's nice, it's happy, it's sorted, it's done. Right? So what I want you guys to do as a bit of you know, extra work is to you know, pause the video right here. Not right now, of course, until just after I finish talking. But I want you to pause the video after I, you know, pause dramatically, or after the beep maybe. And I want you to use the drop and swap method that we just covered to go through and practice with these ions here. Right? So we're starting off with ion 2 and chloride. Right? So how many of each do we need in order to balance it out to 0? Then we've got, you know, copper and fluoride, silver and carbonate, barium and sulfate, silver and oxides, sodium and sulfate, magnesium and chloride, calcium and bromide, iron 3 and chloride, aluminium, and there should be O2 minus down there. That's again a typo. Lovely. It's lovely when you make your own PowerPoints. Calcium and nitrate, as well as lead 2 and sulfide. Alright, so go through, balance them all out, write down what the ionic formulae for each of those should be. Alright, you can pause the video now and give it a go. Thank you very much, and this is Wednesdays with Mr. Longmire.